So welcome back everybody. Our second talk this morning is by Juliet Cooke from the University of Edinburgh, and she will speak on skein categories.
Thank you. Well, I will speak about skein categories coming up. Okay, so the punchline of this talk is by the end of this talk I shall relate skein categories to certain factorisation homologies. So unlike jokes, you can give away the punchline. Okay. But before we do that, I'm going to spend some time defining a skein category because pretty sure none of you know the definition. Maybe? What? Okay, and before we define skein categories, I'm going to define ribbon categories, and the definition is essentially the definition that Turayev gives for the Reshtik and Turayev invariants. So in part of that, he defines ribbon categories. And so if you just he defines them on just the integral squared, but you can kind of easily generalize the definition to a surface. So if you want any details that are being too vague, you can look at his paper / his nice book, which he wrote on invariants of free manifolds, which you'll find it in all the gory details. Okay? So that's my okay, so before we start, we should fix a few things. K, a commutative ring, and to be honest with you, in my head, I'm really just thinking it's C. Okay? But most of this stuff, until I start talking about representations, works for commutative rings with units, so that's fine. And I will script V is a linear. What I mean by that is enriched over K modules. It's strict ribbon. So I mean is I have a monoidal structure, and this monoidal structure is strict, so I don't have to worry about associations and all that annoying nasty stuff. Okay? And by ribbon category, I mean I have a grading which enables me to switch split and spot it in a nice natural way. And I also have a twist. So this is grading. Twist. I have everything has joules, which we had plenty of time discussing last lecture, and everything's and all these structures are compatible. So, because if you've got various structures, they all have to play nicely with each other. So really, what I'm thinking is set V to be the finite dimensional representation. So these are finite dimensional representations of the quantum group. So in that case, we are assuming that K is C, and we're also going to assume that P is not a root unity. So this kind of makes the representation theory nice / boring, depending on your views on the matter and how much you like representation theory. Okay, so this is like the canonical example of V. Okay, so now we've set these things. Oh, and also sigma is going to be a surface, and it's a nice enough surface, so nothing pathological, which actually we've been assuming all week that we haven't got pathological things. So you have okay, so we have a ribbon graph consists of finite numbers of interrupt. Okay, so these are frame directed strands. So what I mean by that is I have a strand, I give it a framing, and I will usually denote a frame strand by a ribbon. Okay, so this is a framing, and I have a base. I have two bases. I have the top and the bottom, which, so this is the bottom, and this is the top. And there's two possible directions. It can the ribbon can go from the bottom to the top, in which case it's positive, the directional orientation is positive, or it can go from the top to the bottom, in which case it's negative. So there's two possible directions to your ribbon. Okay, and we also have coupons. For some simple spaces, you actually can ignore coupons. Okay, so coupons are just things that are homeomorphic to a square. And again, there is a bottom and a top edge, which we kind of distinguish. And when I care, I will mark the bottom by kind of facet, so you can tell which one's the bottom, but I don't think I'll need to spot that. Okay, so we have two things. We have ribbons and coupons. Now we can attach, so if we have a strand, so a base, may be attached I'm probably going too long to the other base of the same ribbon. So basically speaking, we can have kind of annuli like this. Okay, and or to the base of the. So we have coupons, okay, and what we do is we attach strands to them. Sometimes we attach the bottom strand to the bottom strand of the coupon, sometimes it doesn't really matter. We have kind of different options, but in general, you just attach strands to it, and you end up with something like this, and they don't have any orientation.
Only to the bottom and top of the.
Okay, so basically any base can be attached to any base. So you can attach the top base of the coupon to the bottom base, which would be kind of a sensible version, or you can do anything. But I mean, some of this only really matters when you get into the technical annoyances of worrying about direction, which if you're trying to categorify the Kaufman bracket, you can ignore all direction, and that makes life a lot simpler. Well, not categorify. If you're trying to consider the skein category of the Kaufman bracket skein category, that's the word.
So all these lines in sigma cross I?
Which one?
All these things like the sigma cross I?
They will. I'm going to just, so we're going to embed this thing into sigma cross I. I mean, at the moment, they're just kind of abstract things that I've just attached in, you know. Okay, so firstly, I'm going to colour it. So I'm just going to define a colour. So the colouring. So what we do is to our strand, we have some kind of strand, we just attach an object of our category. Doesn't really matter, anyone you like. And so to coupons, okay, so if we have that all of the directions kind of make sense, so the strands pass into the coupon and then out like this. Okay, and suppose we label these with A, B, C, and D. Then this coupon is labelled with a morphism in V from A tensor B to C tensor D. Okay, so that's the symbol case. I'm looking confused.
What's the symbol inside of the ribbon? Is it a V or a wedge? Or
Oh, they're just denoting the direction of the strand.
Okay.
So if you think about it, this has a sort of strand,
Yeah.
and I need to say which direction it's going.
Yep.
If, however, I have, say, the wrong directions, so maybe I've changed, say, this one, these two have the wrong, so say this one has the wrong direction, this one has the right direction, this one has the wrong direction. What I do is I just label it with something. So when things are the wrong direction, we just replace it with the dual. Or the label. So this gives me a labeling. I mean, obviously not depending on what morphisms, it could be that we couldn't actually have such a labeling and then we're just not allowed that kind of coupon in our thing. Okay. So now I'm going to define a ribbon diagram is an embedding of a coloured ribbon graph, again the thing I just defined, into the thickened surface, such that unattached bases, so some of our strands, the bases have been kind of attached to coupons or to themselves, and you have some that are just kind of floating free. We want these ones that are floating free to embed themselves either into the top or the bottom. So, okay, and everything else gets embedded in a little bit. So that's what we got. So in general, we have a surface. So sigma in here is just the disks, and we're going to end up with so if they're attached, we just leave them attached. So we get stuff like this. Okay, and everything has colour. Okay. So now we have these ribbon diagrams, we're going to construct a category of them. So the first thing to notice is that if you consider the intersection of a ribbon diagram with the top of this diagram or the bottom, what you're going to end up is points which have been given a framing which you're going to inherit from the framing of the ribbon, and that they can also inherit a colouring and a direction. So if this one's going up, we say this one's going up. So you end up, so that you can get points just by considering the tops and the bottoms. So this is off. Okay, so ribbon. Is a K-linear, which again just means this is enriched in K-modules. So the objects are going to be finite collections of, so coloured directed points, sigma, and thankfully all this stuff is just added information and they're just basically points in your surface. Okay, and the morphisms are V-coloured ribbon diagrams. Obviously we're go from certain points to certain other points, up to isotopy, which fixes the top and the bottom, so you don't end up with isotopies that change what what objects the function is going to and from, because that would kind of make life hard. And also, these isotopy serves attachments, etc. So what I mean is the isotopy has to keep the orientation, the colouring, and if this is to the left of that, any isotopy has to preserve that, respect that structure. So the isotopies aren't really allowed to break what our ribbon diagram was that we embedded. Okay?
So in the case of tori for sigma equals I cross I,
Yeah.
if I remember correctly, on top or bottom you require the framing to be trivial, like horizontal. So will that cause a subtle difference?
Yeah, there is. It's kind of annoying, yes. When you're attaching to the top, you are assuming that the framing is sort of either directly up or directly down. It doesn't really make a difference for what I'm doing. As I said, there's kind of like a few subtleties which I'm kind of brushing under the carpet because it would take me all day. So yeah, that's I think one of them.
So what was the question meaning? We just have a preferred way to attach ribbons to the top. Is that right?
So I'm saying that like in more classical definition for sigma equals I cross I, if I remember correctly, on top or bottom you require the framing to be fixed like horizontal direction.
Right.
You
So
can
You
have.
need to glue your ribbon as such.
Yes.
Yeah.
Yeah.
So yeah, you do need the framing to be like this because otherwise you end up with allowing half twists, and you don't want half twists. So yeah, you're right. Okay, and the composition. Okay, composition is done by, suppose in this example again, what we do is we thicken our surfaces and we just stack the thickened surfaces on top of each other. So this will define a composition of your ribbon tangles. Obviously this is kind of the trivial example, but you might end up with. Okay. Yeah.
Sorry, this says colored, framed, and directed. Can you say what those mean?
Okay, so the framing means that in practice I've drawn all of these things as ribbons rather than strands,
Right.
and the frame just means they're ribbons pretty much, and that the points are actually like intervals, but you know, because you don't want it, so that's what the framing essentially means. The direction means
Or you say how the interval runs.
yeah, so this is the up or down, that's what it means. So it's either direction upwards or direction downwards.
Oh, but these are the points that are being directed.
Yeah, so what I was saying is from here is that you're given a point, it inherits a colouring and a direction and a framing from the kind of ribbon that's attached to it. And so really this category, the morphisms are the important bit, and the objects are kind of like just hanging around there, being compatible with them. So, which kind of makes sense, because, okay, so now I've defined a ribbon category. Okay, I shall give you the...
Don't you put some relations?
What?
Don't you put some relations?
Oh, yes, I've just put them up to isotopy,
Okay.
fixing the endpoints and the other kind of like directions and stuff. So I'm going to put some skein relations on now. It's
Yeah, that's
kind
what I
of
meant.
complicated to do them all in one go. At this point I'm just defining the ribbon category. And so I'll define the skein category very short.
So your picture didn't show it, but you could have some of those free floating annuli going
Yes,
around.
yes, of course you can. Well, not of course, but yeah, that's quite important because if you have like annuli, so they're good. So you can have like general links as well. I mean, in fact, if you just consider the endomorphisms from nothing to nothing, you'll just get all the links. Okay. So our example, it's kind of an example, but that I sort of discussed before, which is what happens if you just have Toria's example. So you just have a disk, and you have okay, case of this, we actually have more structures, which is we have a monoidal structure. And the monoidal structure is given by stacking sideways. So the composition is done by stacking upwards, and if you can stack sideways, which in this case you can, you have a monoidal structure. We also have a grading, and the grading is done essentially by the kind of natural way. We have a twist, done by twisting ribbons. And we have, and the duality, so when you define duality, you need co-units and units and co-units, and they're given by. Okay, so this is the version that Juliet defines, and all of these structures make it is a ribbon. In fact, this is almost like the kind of why ribbon categories are called ribbon categories. Okay, so
Well, I think your twist didn't actually twist.
Yeah. You need to put the
What
cross
did you
below other in the opposite. Opposite.
Did it not?
Now can I flip it back now?
Okay. Yeah, so
Yes.
yeah. Okay. So now we have a theorem due to derive, which says that you have a functor, which we're going to call eval, which is a functor from this particular F1 into its coloring. And so this is done by taking objects, just get sent to their colouring, and the morphisms, suppose you have a morphism, a coupon and it's coloured by F, we just send it to F, and this is a K-linear, and my ribbon category not K-linear. You can make it K-linear by considering K-linear combinations of ribbon diagrams. So in this category it's actually K-linear, so this is a K-linear ribbon functor. And what I mean by a ribbon functor is it respects all of these ribbon structures. So this functor sends this to the monoidal product E and V, the braiding to the braiding in V, and the twist to the twist in V, and the co-units are sent to it. I mean, this is essentially necessary to make it a ribbon functor, and this functor is surjective. It is not necessarily faithful. In fact, usually, very rarely, in fact, never will it be faithful. Okay? So now I'm ready to define my skein category. And which I'm going to do a little bit hand wavy, but
Is there a way to describe this system using some universal property?
Really helpful universal property called factorisation homology that you'll get to at the top.
Yeah.
It's a really good characterization.
Exactly. Right. But for the moment, we'll just stay nice and concrete with pictures, because I like pictures. Okay, so definition. The skein category is this ribbon category with a relation on the morphisms. Okay, so suppose I have two morphisms, F and G. These are k-linear combinations of ribbon tangles. These are related if, okay, so we need to have so we have ourselves a surface across a pencil, and this is where all of the ribbon diagrams live. What we want to do is we want to embed a cube into this surface. Okay, so we're just considering this cube embedded in the surface, and the cube has to not flip. So it's going to an orientated embedding.
Cube in the surface cross out.
Yeah, cube in the surface cross the interval. That's the one. Okay, so this is this cube, and we're going to also assume that this cube intersects the ribbon diagrams in F and G quite nicely. So it only intersects along the top and the bottom of the train, and that's just only in transverse straights. But that's fine. So if we have such an embedding, and F equals G outside the cube, and eval, so our eval function which we define here, if we restrict F to cube and we evaluate it, we get the same thing. So basically, this is essentially a kind of skein. It's essentially they satisfy, the skein relations are determined by the things which are sent to the same thing by eval.
So suppose I did something stupid and I plugged in like a symmetric monoidal category for V, then this would mean suddenly all my braids can like move through each other. Is that right?
Yeah, it should be. Yes.
Because I think
Because
it's
that's
closely
the
associated to
That's not real. It'll go away in a minute.
That's the final answer that they wondered about on Monday.
Yeah.
Oh yeah, right. So if you put the symmetric monoidal, it would kill this way. They can just say strands can move through each other, which would make a rather boring thing. But I mean, you know, it would work. Okay, so I'm now going to.
And then you do some transitive closure of that.
What?
And you take like a transitive closure of that.
I've never really thought about what happens if you put in the symmetric monoidal one. I've been thinking about a certain example, which I'm just going to put in the ball, which kind of, for me, is, you know, okay, so I am now going to, you know when I said at the beginning that I was really thinking of refugee, and I'm just going to consider what happens if you stick in these representations, finite dimensional representations of the quantum group SL2. Okay? Okay, in which case, this relation kills coupons. So every time you have a coupon, you can just replace it by standard some kind of multiple of just a strand without coupons, and you can also get rid of the directions, which is essentially analogous to why you can get rid of directions in Kaufman bracket skein algebras. And you have two relations. You have this. Hopefully my left and right are correct. I'm sure someone will tell me if they're not. Anyone recognize this? Hopefully some of you do. Okay, these are the Kaufman skein relations.
not sure if kill is the best word.
Yeah, it's a bit violent, isn't it?
No. It becomes a multiplier.
Yeah, so it just becomes a multiplier. So you can essentially.
So let me clarify
Yeah.
Peter's question. So I think what you mean to say is by Schrodel duality, every morphism is represented by every morphism, which would be some abstract coupon, can be written in terms of braids. And so it's not that it kills them, it's that
Yeah,
you don't need them.
Yeah, we
Right,
don't need
yeah,
those.
Kills would
Yeah.
imply they go to zero.
Yeah, that's what I
So,
meant.
okay, can remove using the relation. Okay,
Right.
so what do we have in this example? So we've removed a lot of the fanciness that I spent the last half an hour trying to describe. But anyway. Okay. So we have.
I mean, you should maybe point out that these are no longer labeled by any V. I mean, it's only the standard representation.
Yeah, so this is. Yeah, so if you want
So
just
if they're
this.
actually labeled by some V, then you don't have these relations, right?
Yeah, you don't want to label them. You want to just use the standard representation.
So also the objects now have become.
That's right, so you could say removes coupons, directions, and all colorings. That's true, that's the concept of Schrodel.
Yeah. So what we end up with is we have.
So what do you mean by remove coloring? I mean relation, isomorphic relation.
The only allowed V now is the standard representation.
But this
Not even
relation
the dual.
allowed to touch the sigma 0, sigma 1. I mean, is the relation only sits inside or okay.
What these?
No, that
This-
equivalence relation. Can the cube like touch the top or
No.
the bottom?
The cube. Yes.
Well, it doesn't matter, I think.
It doesn't matter because the
Oh,
cube.
it's slightly away.
Yeah. So we. Yes.
Yeah, just, I don't understand what does it mean to remove the color. Okay, yeah, I'll ask questions.
I mean, the colours are essentially, if you can remove them from the tangles, you can remove the.
It's not so much to remove them, you just get to use the color standard representation of SL2 as opposed to n-dimensional representation of SL2. You just make them all the same color because
Okay.
So these are. This is an equivalence relation, which I'm just saying is that you can always use this equivalent relation to like colouring with standard representation, so you don't need to keep that information around. Okay, so we have a calculate of tangles. So in general we have all our annuli. Could be, and we have ribbons that kind of from the top to the bottom. Okay, subject to the Keltman. So from that, you would conclude that if you wanted to consider the Homs from nothing to nothing, you just end up with the Keltman bracket skein. And this is a sort of motivating example for why this thing would be called a skein category in the first place. So I've now hopefully kind of described this category, right? And so now we're going to move on to some properties about this thing. And hopefully we should get to factorisation, homology. Why isn't this hopefully?
Can I make sure I understand the content of this example?
Okay.
So when I'm removing the colorings, you're just telling me I can put all the simple reps into one.
So I can remove the colours with the kind of boring colouring, and then I have a boring colouring. I just don't bother colouring it up.
Not one. Yeah, I mean, there's the standard one, so like, I might have a lot of strands of different colors, but I can like map them all into the standard.
Yeah.
Okay.
first thing to realise is we have a function. So this skein thing, which takes some kind of manifold, which is two-dimensional and framed, and it takes it to K. Now cat K consists of, so cat K is essentially the cat which we had this morning, but except now everything is K-linear. So it's the objects are small linear cats. It's morphisms are K-linear functors. And it's one morphism. It's two morphisms. Are K-linear natural isomorphisms. And then we stop. Which I think we didn't do this morning. So we have literally just so this thing is a two category.
I can't read your handwriting because the domain there.
Which bit?
What's going into cat K? I just can't read
Okay,
your handwriting.
that's manifold.
Uh-huh.
So this is manifold. So its surface is framed. So the same manifold as we have had so far this week, but just two dimensions, which is why we're stopping at the two morphisms. So we just have a two category. It's a K-linear two category. Oh no, it's just the two category. Sorry. I shall not start saying something that's too long. Okay, so if you have a surface, it assigns the skein category to the surface. The colour skein category. If you have embeddings of manifolds, this will actually define. So an embedding of a manifold defines an embedding of a fitting manifold, so you can see how you would translate between the two different skein categories using this embedding. And you also have natural isomorphisms. You could also move that over the other side, and the reason being is isomorphisms of embeddings essentially map out ribbons, and you can think a bit about where the isomorphism would be set to. Okay, so given this thing, so we have a functor.
So two morphisms would be isotopes or what?
So yeah, they are natural isomorphisms.
On the left. On the left.
In here, yes. So in here they would be isotopes.
Thank you.
Of embeddings.
So do you really need a framing?
I wouldn't like to get rid of it right at this moment. I think in skein categories you are assuming that there's a framing because you've been putting framing on a span and there's the whole conversation about not knowing half the twists. So
here I didn't get into orientations very much, but the twist, the ribbon structure allows you to get rid of the framing. So what you wrote is correct, but also Gregor is correct that you could replace it with oriented and you would still have a functor.
Yeah, I believe David, but I'm not going to start claiming this right now because I haven't actually given any thought to it. Which probably makes it a good question. Okay, so right, we have some nice simple facts about this thing. Okay, so we're going to start with a couple of nice easy things, which is that kind of, I should have mentioned before, but if you stick in our disk, we have essentially just said that this thing is going to be isomorphic here because this is essentially how we define our relation, which is to force this on the disk. We also have that if we have, so if we consider A, and we consider it to be, and this is just like some point manifold. Okay, so I'm just going to give you an example. We have a natural monoidal structure on this, which is given by just using our trivial direction. Okay, so just in this example, which is just S1 example, we just sticking the cylinders together and embedding them into another cylinder, and that will define it as a monoidal structure.
Are you assuming this functor is monoidal with respect to constraint U?
Which one? This functor? Yes. Yeah. That's easy enough because you can just make them just stick to each other. Monoidal. Okay, so the reason why this is important is that a monoidal structure, as we heard from this morning, means that it has an E1 algebra structure. Which may not mean anything to you now, but I need it right for the expert. I thought I would just introduce it before I forget. Okay. Now I'm now going to get on to a certain other interesting property on this, which is I said that this scaling category is essentially a factorisation homology in fancy clothing. And the important thing about factorisation homology is that it satisfies excision. So if I have any chance of that claim to be true, this thing must satisfy excision, and it must satisfy the exact same notion of excision, which is the notion we use in factorisation homology. Okay? So, I'm going to talk about excision. So, what we need for excision, we need is, so we said that this has a monoidal structure. We also need some actions of, say, this thing into just the general surface. So suppose it has another boundary component, it doesn't really matter. And so we have two embeddings on the left. And what this embedding does is, on the same surface, it squishes this manifold out of the way a bit and includes this. And in general, you can kind of generalize this to slightly other surfaces, like if you want an interval cross-spacing, same way. And again, we have another map which does the same on the right-hand side, which takes n and isocopies it out of the way a bit, and then we embed that thing. Okay, so what does that mean? It means that, oh dear, I should probably not start like this. What it means is that skein M is a right. And I've just told you what the action is. And
Because an embedding through this functor gives us the action map.
yeah, so this little triangle is our action map, basically. And it's acting from this bit. And we also have this on the right side. Okay, so we have this middle thing. We've got two module structures. And I'm gonna, just for notation, just write this. I'm going to use script to refer to the skein category. And now we define the local tensor product. How we would in factorisation homology. So, because of these actions, we have a relative tensor product. So, okay, and technically speaking, this is defined to be the two-sided bar construction, which is the co-limit of, so you have three copies, so this is the skein category of A, etc. You end up with this map, and this will take you to, you also can act on these, and you can make one copy, or you can act on the left, like this, and given these, you now have two maps. And so we define this, and because we have two categories, we stop at the second stage. So this is the okay, and also technically there's a few two stages, but we won't worry about those. So this relative tensor product is the co-limit in cat K of this diagram.
Sorry, can you say exactly what the monoidal or symmetric monoidal structure is? Cat K cross?
That's
So
just
you
the
take
Cartesian product of category.
You
Just
take the product of object sets?
Yeah, so
And
the
you take the product
yeah, so you're
of
just
Homs?
taking tuples basically.
Yeah, but Homs.
On Homs, it's just also tuples. Just kind of a like boring.
Tensor product.
Yeah. So what?
Tensor product of Homs.
The tensor product of Homs. Oh yeah. So you define it to be you define it essentially by taking the tuples of things in M and things in N.
Yeah.
Yeah, so you can just move
His question
silence
is
through the
that
tuple.
his question is that you take product on objects and you take tensor product on Homs.
Yes. Yeah. No, that makes sense.
Okay.
Yeah. You're right. Sorry. I'm not very good at thinking on my feet. Which is fun. Talks. Alright, so we've defined this skein, this relative transfer, and this is the definition which was used all this week that no one actually bothered going into all the detail. And so I'm just going to state that we're right. So we have that in the situation we've described, we have that the collar gluing of N, there's an equivalence of categories between this and this relative tensor product. I've kind of dropped the V's, but they're in there somewhere. We define this by just defining literally a functor from here to here, and the functor is given by, suppose I have this color gluing, so I just embed M into the left, and into the right, and then we're just going to work out this on that stuff, but I'm not going to go into that. So it's just nice little block cuts. Where did I use my block? Okay, and so that is number 3. So if I left this thing over here, I said if this satisfies 1, this satisfies 2, and this satisfies 3. And those 3 facts about a certain functor actually fully categorize a factorisation homology. So if you have a functor like this, satisfying essentially 1, 2, and 3, it is a factorisation homology, which, you know, you're just going to have to accept. But it kind of makes sense. Right? Homology theories tend to be characterised by certain properties that they satisfy. Okay, so I should probably just do that.
Is it easy to articulate what the hardest part of proving that theorem is?
What?
Is it easy to articulate what was the most difficult
Okay,
part of
so
proving that?
this comes in 2 stages. What you have to do first is you have to prove that this co-limit is in fact equivalent to a relative tensor product, which is just the relative tensor product of k-linear categories. So it just has kind of objects in here, morphisms in here, and just tuples and morphisms. And it also has a bunch of isomorphisms. And what the isomorphisms do is essentially they're needed to relate the action of A on here to the action of A on there. And so you have to prove that this thing is equal to that definition of relative tensor product. And then with that definition, you can then construct a functor f from here to here, and then you just kind of by hand show that this thing is in back in equivalence. So that's essentially what is going on in the proof.
And why was it important to begin with the two-sided graph rather than the
Sorry, say that again?
and why was it important to begin with the two-sided graph rather than this?
Because this is, when I say that the thing, so when factorization homologies are characterized by satisfying excision, then the definition of relative tensor product used in that statement is this definition. So if I just cooked up a random relative tensor over it and said, you will believe that this is the correct notion of relative tensor product, then there would have been a rather big miss indeed. Yep.
May I ask who is this theorem?
Me. When I finish writing it up. Okay. Okay, so the conclusion is skein, this functor here, yes, is linear factorization of homology. So call this which takes so that's the conclusion. So we have just factorization homology, which is in k-linear categories. So it's essentially an enriched two category version of factorization homology, and that works perfectly fine.
I think you want one of the dashes to be V.
Yes, I do. And what we said earlier was that if you have a braided, you can define an E2 algebra using a braided monoidal category. And V is a Riemann category, so it's a braided monoidal category, so it defines the E2 algebra, and that's how it's defined. And just in the next 5 minutes, I shall explain a slight thing which relates to how this relates to the next talk, and also, I guess, where this started, because I didn't actually start with k-linear categories at all. Okay, so if you take this thing, you take this on the surface, choose your favourite surface, and you take the free completion. So what you do is you throw in all of the co-limits that this category happens to be missing. You throw them all in, get yourself a nice co-complete category. And this category, what you end up with is another factorization homology. And so I will describe which factorization homology this is. Oh, yeah. I need to choose. Yeah. Okay, so that's the general statement. In practice, what I want to do is I want to consider just my.
Well, what's written at the top there?
PR. I will describe what PR is just in a second. Okay, so if I take finite dimensional representations of the quantum group G, what I end up with is the presentable factorization homology of integrable, so like no longer finite necessarily, but not so horrendous. Well, integrable ones of the same quantum group. So okay, so PR is.
So maybe on the left you want to write. You were started to write cat when you.
So if you take the free completion of this thing and this thing I've just said is I'm really not strong enough for this. is the refugee coloured skein category of the surface, what you end up with is this thing. Now this factorisation homology is the factorisation homology in the kind of universe that we'll be talking in the next lecture, and this is actually the factorisation homology I kind of started off by considering. And PR is again a 2 category. Linear. It no longer consists necessarily of small categories, but they have to be presentable. Okay, so presentable linear categories. So in particular, that presentable means that they are co-complete, and a few other things, they're not too horrendously large, because otherwise you end up with set theory issues which you don't want to get into. And the morphisms, so you have co-continuous functors, and the 2 morphisms are just going to be natural isomorphisms.
And when you say 2 factorization homologies are the same, you need to clarify what you mean by the same.
I mean that these are equivalent categories. And I think
integrable that's not finite dimensional, just an infinite direct sum of it.
yeah, so it's an infinite direct sum of whatever it is. Anyway, I think that's basically me done. So is there any questions?
Okay, so do we have questions or comments for Juliet?
So if you plug in G equals to SL2, you get back like usual Kaufman bracket skein algebra. You also have like Humphrey skein algebra.
Yeah, you want to
can
plug in
something
SLN for that, I think.
like all SLNs and then
I think
fancy or
I've not actually looked at this, I just feel that SLN is the right answer. You know?
Yeah, so if you take the specialization of Humphrey corresponding to SLN, then of course her theorem applies. There's a sort of what people sometimes write as SL lambda, where you sort of this interpolation where lambda is a polynomial, and then if you so that has a quantization rep q SL lambda, and that thing its factorization homology will be the Humphrey.
More other questions or comments from here?
So, I feel like I still don't understand the universal property of the Ribbon version. Like you presented it as an extension of the skein version with a kernel and some sense. Actually, I don't even know what the kernel is. The relation that you modded out by was essentially the kernel, but I don't. David said, "Oh, if only there were factorization homology," but I feel like it didn't quite capture. The only reason I ask is because this seems rather formal. If I wanted to replace k-linear 1 categories by something else, I was wondering to what extent you can actually start claiming things about ribbons labeled by blah and then blah.
I mean, the reason why it's in Cat K is because just the skein category is just got to do with colouring, whatever its colour is. I guess if you started colouring it with something that was instead of a k-linear ribbon category A, something else enriched ribbon category, you could maybe do something slightly different, but I've not really considered a something else enriched ribbon category.
Is there an adjoint to your evaluation functor? For the case of the square?
No, there is a. Okay, so if you want to start with the which one, the free one or
the one that you erased maybe 45 minutes ago.
it was right
ribbon
there.
V of the square maps to V by evaluation.
I'm actually not sure. I mean, that's just derived, so if it is, it will be probably be worked out by hand.
That is actually the universal property of ribbon
exactly.
categories. Maybe that would be an answer to your question.
Which exists. So there is V maps into this ribbon category, and it maps out of it. And if you have some like ribbon functor, it needs to either guess that one, it needs to factor through the other one, which is something like coherence for ribbon.
I think one way to formulate, I'm not sure if what I'm saying is correct, but apparently this ribbon V can be defined for quite general category V. So this ribbon will give a monad on the category of all small categories, and this monad define ribbon category.
Ribbon structures are monadic over just categories.
I think something along this line.
So this is like a free ribbon category generated by these labels.
I
When you
think
write ribbon,
So,
this is the free ribbon category.
Yeah, you can do it that way, yeah.
do we have some more quick questions,
I have one question.
but not comments?
So in this free of factorisation homology is factorisation homology?
Yeah.
What is the meat of the statement here?
Well, essentially, it's literally just following from this, which is essentially factorisation homology is just the limits dressed up fancy, and you just end up, and free co-completion is just it's actually just a kind of corollary.
That's a formal property of free being nice. That you get.
Yeah, and I mean, you can go the other way. If you start with rep, QG, and you take adjectives, you don't quite end up with a skein category, you end up with an item present completion of the skein category, which we were thinking for a while to make as the definition of the skein category, but we changed our mind. So, yeah, it's just essentially a corollary, but one that might be enlightening to some people.
Can I ask one short question? On the right-hand side,
Yeah.
if you plug in signaling equals a disk, is there a Verma module in there?
Which one?
A Verma module?
I don't know what a Verma module is.
Okay.
A Verma module.
Oh, Verma, yeah. I don't know. That's still beyond me.
No, it's just direct sums of finite dimensional representations.
So I have some questions as well, but I think I will not ask them. And I think we should meet again maybe at 10 past or quarter past. What do you think? David?
Yeah, 10 past is fine.
Let's try to meet at 10 past. Is that enough time to go to
Or quarter past is fine.
quarter past?
Yeah,
Okay.
Let's
We'll
meet
meet
at 1
again at
o'clock.
quarter past according to this. And please note that the clock outside is wrong. So we meet at quarter past according to this clock. And let's thank Juliet again for the talk.